and 43.
Okay. 44 and 43. So let's look at that. Okay. Let me look. That's 43. I'm going to go ahead and grab 43 and 44 is what you said, right?
Yes, sir.
Okay. All right. All right. So first things first is we're going to make we're going to let x plus 5 be equal to g. Okay. So this is really going to be g squared minus 3g minus 4 equal to 0. Okay. When we do that, what it allowed me to do is take a crazy quadratic and rewrite it in terms of something that was it's a little bit easier. And from here, we can solve it by factoring. So it's 1 times negative 4, which would be negative 4. And then that's negative 3. So factors of 4, when added together, give you 3 as 4 and 1, right? So the 4 has to be negative because when you add it, it's got to give you a negative 3. So negative 4 plus 1 is negative 3. And then if we multiplied it, negative 4 times 1 will give me negative 4. So let me do this. Maybe spotlight. Yeah. All right. So can you see that spotlight? Can you see that little thing on the screen?
No, I can't see it.
No?
Mm-mm.
No, not at all. Okay, I'll turn it back off. Boom. Okay. So what we've got is x minus 4 and then x plus 1 equal to 0. And we will turn around and set these all individually equal to 0, these factors. And so we get x equal to 4 and then x equal to negative 1, right? So we took it to a simple little quadratic. Now that we've got what x is, I used x, it should have been what? G, right? G is equal to x plus 5, so I can substitute x plus 5, so I can minus that. So x is equal to negative 1, and then I can change it over here and go g is x plus 5, so minus 5, x is equal to negative 6. Okay. Did we do me that? So all right. So we've got there's 3 of us, Sarah and Bree and myself. So all right. So Sarah, that gives you a little bit more of an overview of what we are kind of looking at. Let me make this right here go down. X. There we go. Close Alt tab. All right. So what other ones do you need?
Can you do 56?
56. Yep. Let's see. Domain and range?
Yes.
Okay. So the domain is going to be negative 3, right, to 2. Let me grab. this, and that way I can write it out. I can do it in two forms. So there we go. So the domain would be -3, 2, or it would be between this, right? Set notation, interval notation, right? It's a bracket. And then the range would be from -5. And it's always smallest to largest, right? Not bad, pretty good. Yeah. Riley's and Isaac are working on a painting project for school for one of his classes. So she had to paint a tile, 2x2 tile. She's done pretty good. All right, so the range would be -5 to, let's see, to 4, right? Clean that up a little bit.
So would the domain be what's on the X value and then the range be what's on the Y?
Yeah. So here's the X values for the
This
domain.
confuses me more than anything.
Yeah, and then the range is Y values, right? You got to know, you're going to have to know what the range is for this right here. Right. So if we do, this is absolute value, right? We know it's at 0, right? So it'd be 0. If we was looking at the range, that's the Y values, right? 0 to infinity. Because the domain on this would go from -infinity to +infinity, right? If it does that little thing. Yeah. There you go. All right. I'd make sure I could do that. So, we've talked about absolute value and stuff like that, and we've talked about domain and range of different things, but make sure you can do that. The formula sheet does not have eyes or the perimeter. Are there any other formulas we should remember? The perimeter is just 2 times the length plus 2 times the width. So make sure you can solve a cubed equation, right? A cubed equation, kind of like if it's a cube root equals negative, or cube root equals anything, I guess you'd want to raise everything to the third power, right? Let me see. Cubed and squared equations. Make sure you can do those. I squared, if you multiply complex numbers, you got I squared, which is -1. Where you have to make sure you understand that. But no, got to make sure you can write an exponential equation given 2 points. Definitely got to know how to do that. So, yeah, I think you're okay. I think everything else that we've talked about should be okay. So, hopefully that answers your questions. All right, Sarah, what you got?
Let me look.
Okay.
What about 63?
If you were to do that, then you just find the slopes, right? Now you are going to have to probably write an equation of a linear equation given that one is parallel, like 65. I'd make sure I could do 65. 63 hinges on the same concept of 65. So let's look at this. You grab this one. Okay. So if I got to look at this, I got to determine, well, the first one's easy right here because it's almost in slope-intercept form, but it's got a negative right there. So that would give me y equals negative 8x minus 1. And then the other one here, I'd have to take and put in slope-intercept form, which I would have to move my x over, get 3y equals negative x plus 12, and then divide each side by 3. So I'd have y equals negative 1/3 x plus 4, right? For parallel lines, the slope of these two would have to be the same. We know that that is negative 8, and this is negative 1/3. So that can't be true because they're not the same. Perpendicular would mean that one would have to be positive, the other one would have to be negative, but they'd have to be the reciprocals of one another. So this is negative 1/3. The only way I get something perpendicular to that is if I had the other one be positive 3, but it's negative 8. And vice versa, if I got negative 8, then to make it perpendicular, I'd have to do positive 1/8, right? So this would actually be a neither. So, but 65 is probably what I'd look at. I'd make sure I could do number 65. I can't remember if there's a problem now to write the equation of two exponentials. I'm not sure if it is or not. Maybe y'all could tell me. But I know we did two of them in class. I taught one of them and I allowed y'all to try one of them, and that would have been in 6.1, right? I think that was 6.1. So make sure that you can do that. All right. You good with that, Sarah?
Yes, thank you.
Okay. All right, Bree, you got one? You just hanging out? Can we review transformations? Yeah. You'd want to know the transformations that I would make sure that I could do would happen to do with this, and it would be right. So I'd make sure I could do it on quadratic. If you walk it from left to right, this is going to be a reflection about the y-axis, right? So the parabola, instead of opening up, it would open down, okay? This, the green, would be it's really the absolute value of A, so that's 2, and that would be your vertical stretch, by a factor of 2, right? Vertical stretch. And then we'd have a, let's see what I can grab a purple there. This, which is inside the function. So you're looking at, that's a positive 3. So you're really looking at left 3. And then let's grab that one. So this one would be up 4. Okay, so you look at a quadratic. Can you do that to a quadratic? Can you understand what is happening there? And really, the only thing you know, if I were you, I would look at focusing at get back here, there. I would look at taking something like this and doing just to practice my transformations. I would just do Desmos, and just so I could see based off the equation what's really happening. So we go like y equals x squared, right? Okay. What do we have? So that's the parent function, right? So we're going to hit, we had -2 times x plus 3 squared plus 4, right? I think that was it, right? Didn't we do that? Pretty sure. Yeah. So you can kind of see, okay, it's being reflected. The vertex is being moved to the left 3 and up 4, right? And it's actually a little bit narrower. You know, if we just, and so you, how do you know it's narrower? Then just do this: -x plus 3 raised to the second plus 4, right? So you can see that that's the green one. You saw the blue one, the 2, what it does to it, it's a stretch. It makes it get closer to itself. Like if you take your arms and raise them up and get them closer, try to clap your hands above your head. As it's extended your arms, your body's stretching. So that's kind of what the A, if it's bigger than 1, is going to do for a vertical stretch. If it's between 0 and 1, you would have a compression or a stretch and compression. So stretch and shrink. So that's what I would do. Okay, just kind of look at it. Just evaluate quadratics on Desmos, and I think you'll be okay. So does that help you a little bit more?
Yes, thank you.
Yeah. All right. What is next? What would y'all like to do next?
Can we do a few different word problems?
Yeah, we can do. Talk to me. Tell me what you want to do. And I'll tell you if it's yay or nay, whether it's one you might want to look at or not look at, or.
Can we go ahead and do 67?
Mm-hmm. Sure can. All right, a clothing business finds that there's a linear relationship between the number of shirts N it can sell and the price P that it can charge per shirt. So what you have to understand is you've got an input and you've got an output, right? So the input is N, which is what? It is the number of shirts, right? And the output is P, which is basically how much does each shirt price per shirt, right? So kind of understand that that's what you're looking at. It says in particular, historical data shows that 1,000 shirts can be sold at a price of $30 and 3,000 shirts can be sold at a price of $22. So folks, what you have to understand is that this is that's 30. And then 3,000 is at 22. These are ordered pairs. They give you 4 bits of information, right? And if you look at that, you know, it's like here, there, and there. 4 bits is going to be 2 ordered pairs always, okay? 3 bits will be a slope in the ordered pair. 2 bits of data will be slope in the y-intercept, okay, starting point. So it's kind of how that set is set up in a linear. From here, all you have to do is basically find slope, right? So I'm going to do slope 2 ways just in case, you know, there's people out there. So 1,000, 3,000 is an increase of 2,000. 30 to 22 is a decrease of 8, right? So we would have, if we did slope, it'd be -8 over 2,000, which is, I don't have my calculator over here, and I'm about to get it. So let's see. -8 divided by 2,000. Yeah, I want that as a fraction. So that would be -1 over 250, right? But if we did, you know, if we did slope traditionally like this, and everything, we'd say that's x1, y1. This is x2, y2. Then we would go, what, 22 minus 30 over 3,000 minus 1,000. And we'd still get -8 over 2,000, right? So there, that kind of shows you how you get the slope 2 ways, right? So now that you got the slope and you've got 2 points, you write the equation. And what I normally write the equation in is in point slope form, which I think is the easiest way to do it, because you plug it in, and when you get done evaluating it, you have the slope intercept form. So pick any points you want, because either point will work, because there are points on the line. So I'm going to pick the 1,000 and then 30. Just note when you plug the points in that they have to change signs, because you've got minus y1 and minus x1. So that would be y minus 30, because 30 is positive up here, equals -1/2 over 250 x minus 1,000, right? So, and if we go ahead and distribute this, we get equals -1 over 250 x. That would be times -1,000. That would just be plus 4. So we have y minus 30 over here, and then we just add 30. So that would leave us y equals -1 over 250 x plus 34. Okay, so there you go. That's how you would do that. All right. And really, this content of taking 2 points and writing an equation and finding slope, all that stuff, are basic fundamental skills that you need to make sure you're good on linears, right? Okay. All right. So, any questions on that one? Anybody? Just remember that you know, it's not open-ended; it's multiple choice. So as you get going, you ought to be able to, when you get done working the problem, you'll be able to look at it and find your answer. Okay. So I don't Can't remember who asked this one, if it was Bree or if it was Sarah. So just let me know what you got. Okay. All right. Your calculator. Now, if you plug this in your calculator should be able to show you, should be able to do this calculation pretty easy, because it'll do scientific, but we're going to do it by hand. So this is going to be, before we do anything, this is going to be 10 to the negative 20, right? Okay. So we got 10 to the 6 over 10 to the negative 20, and that would be 10 to the 6 minus 20, which you subtract the negative, it becomes a positive. So that's 10 raised to 26, which would be whatever that comes out to be. I'm not sure what form they wanted us to leave it in. Yeah, just 10 out of 26, or 10 raised to 26, I should say. Yeah, just like that. They use the properties of exponents. So really not so much for that problem number 1 for scientific. 2, 3, 4 are really good for scientific. Know how to write it in and take it out, right? So, and I worked some problems like that on the video last night. So, all right. So 86 and 87. So let's do this thing. I'm gonna grab both of them real quick. 87 real quick while we're doing this. All right. So looking at this, condense it. Expanding means to spread out. Condensing means to put back together. So we have two logs that are separated by a plus, which means that they are multiplied by one another, which would give me log of 2x to the 4th times 3x to the 5th, right? Well, we know that because we can do something because those are multiplying, this gives me log of 6, and that's x to the 4th, x to the 5th, which gives me x to the 9th. Okay, so that's what that should simplify to. And if we look at that, just kind of make sure not out in left field on that. Go over here and look at 86, make sure. Boom, boom. Have I missed anything? Yep, there you go. So they just sat here and multiplied these together and got the same thing that we did. So I always like to double check when it's not my review. So 87. This one right here is separated by a subtraction, then it's separated by a plus. So what are we going to do? So this would be log of x, but I got to move this up, right? So that'd be over the square root of y, because this would be log of y to the 1/2, and we know that if you got a fraction of a power, that it's really a radical. The base is the root, the denominator, I should say, not the base. The denominator of the fraction is the root, and the numerator is the power. So really, that's what you've got. Now that's still plus 3 log of z, right? So if you think about that, this becomes the power, right? And it's multiplied. So this all simplifies down to xz all over square root of y. So I guess you could have moved this one out to the end if you wanted to. If you wanted to say, hey, log of x plus 3 log of z minus 1/2 log of y. The commutative property of multiplication, not multiplication, of addition will allow you to be able to do that as well. So, all right. So let's see what else we got. You good on that? When you're looking at this one, it's saying if an investor invests $23,000 into 2 bonds, one pays 4% in simple interest, and the other one pays 2%, and the investor earns $710. How much was invested in each account, right? I equals PRT. So you've got account 1. Well, its P is we don't know. Its R is we're going to say 4%, right? And the T, we're just going to say it didn't say because we're going to be the same on both of them. So we're just going to say 1. Okay. Doesn't really matter because we're not differentiating, longer in one account than the other one. Still don't know what we got on principal here, but this one is 0.02%. And of course, we make the time 1. So how do we know how much they put in each account? So we're going to put X amount in the first account, and then we will do 23,000 minus X, because that would give us, let's say we put, if X came out to be 10,000, so 10,000 in first one, and then 23,000 minus 10,000 is 13,000, right? So that's kind of how this little algebraic technique. You tell me how much you got, but I got to split it between two things. I'm going to say 1's X, and then the total minus X will give me the other amount. So all we're going to do is set this up. But I'm going to put equals I over here. So I'm going to move that to that side. So I'm going to say, okay, X times 0.04, right? We're going to say for 1 year, plus 23,000 minus X, times 0.02. We're going to say it's for 1 year. And he earned $710. So this is the equation. It's, splitting it. So this is 0.04x. Then we're going to distribute this. And we'll do, what's 23,000 times 0.02. And that gives me $460. So it's plus negative 0.02x, because that, and then times 1 is 710. If we add these, so go ahead and combine my like terms here and here. So that would be a plus. Yeah, let me do that again. 0.04 plus negative 0.02 is 0.02. 0.02x plus 460 equals 710 minus 460. Okay, so this would be 0.02x equals 710 minus 460 is 250. And of course, divide that, right? That's, so that divided by 0.02 gives me 12,500. So we got 12,500 going into account 1, right? Which is at 4%. Here's X, right? Right here. So it's 4%. So the account 1, 4% is 12,500 of that 23,000. And if we want to count at 2%, that would be 23,000 minus 12,500. And we get a total of $10,500. So that's kind of what you do on that one. And you'll have one that has simple interest or linear. You know, I'd make sure I could do that. Okay. So because it's a fraction underneath a square root, really what you can do is split it, right? But I want to show you something. If I go ahead and split this, then I'm going to probably, well, not so much in the bottom, because that's a m squared, but is 361, is that a perfect square? And that I don't know. I think it is, maybe 19 maybe. Yep, it is 19. So 361 is a perfect square, 81 is a perfect square. So if you're looking at this, let's take care of the bottom one first. So that's 19m over square root of 81 is 9, and then I have to leave the m in there. I guess I could have took, if I took that away, then I'd have to rationalize, so I wouldn't want to have done anything here. You know, like got one up here and then take one away. That would left me with square root in the denominator, and we wouldn't want to do that. So just kind of recognize that I can split it. This was m squared, so that's great. I didn't got to worry about doing, you know, it would come out because it's a pair of 2, and then 361 is a perfect square. Okay, so hopefully that helps. All right, so a ball is thrown in the air from top of a building. Its height is in meters above the ground as a function of time. So time is the input and the height is the output in meters, right? All right, so here's the equation. How long does it take to reach its maximum height? And how long does it take to fall to the ground? Well, these are two separate problems because we have negative 4.9 t squared plus 24t plus 8. So the first thing you need to do, maximum height, that'd be the vertex, right? H equals negative b over 2a. So we're going to say negative 1 times 24 over 2 times negative 4.9. And that's going to get negative 24 over 2 times 4.9 is negative 9.8. So that's going to be 24 divided by 9.8. That's 2.449. So that's how many seconds it took, right? So then we're going to plug that back into our equation. So 4.9 times 2.449 squared plus 24 times 2.449 plus 8, and that's going to give us, well, let's type it in and see what it does give us. So negative 4.9 times 2.499 squared plus 24 times 2.449 and then plus 8. What that gives us is this. It gives us 37.3878. So how long did it take to reach its maximum height? Well, it only took 2.449 seconds, and its maximum height happened to be 37.3878 meters. So they only wanted the first one, but I went ahead and showed you how to find the vertex of it. Now, how long does it take to fall to the ground? Well, that's just a quadratic formula, and what I'm going to do is just going to refer back to looking at 72 right here as it's worked. Let's see, 72, where you at? Yeah, right here. There we go. And this, I'll just move this on down. So here's the quadratic formula. It's all plugged in. You'll get negative 0.31 and then 5.21. Of course, you can't have negative time, so this answer goes away, and it'd be 5.21 seconds when it hits back on the ground. Okay, so that one, yeah, you need to know how to do evaluating quadratics, change them back into both forms, stuff like that. So, and solving them. So that's a good problem. All right, ladies and gentlemen, that's it. So I'm gonna hit this stop.